Everybody, we've made a quick host change over the last session. My name is Jorrit Meijer, and I will be hosting the next few sessions together with Esther. Maybe a short introduction is in order, Esther.
Well, for those of you who missed the opening session, I'm Esther Bartel. I'm a technical consultant, end-user computing background, and currently switching to DevOps and cloud DevOps.
My name is Jorrit Meijer. I am a co-organizer of Azure Thursday Meetup, and we are also organizing this event today here from the studio. It's very nice to be here. My first time on an event like this, but yeah, I'm looking forward to the next sessions. So the next session will be from Erwin Staal, and I don't know if he's already in the session, but let's bring him in.
I am, yes.
Hi, Erwin. How are you?
Hi, good afternoon. Fine, thank you.
Great. So yeah, I've read something about you, and so I've seen that you're calling yourself a DevOps engineer, but also an architect, which really is interesting to me. So how do you make that work?
Well, what I like to do in my job is I always like to be in multiple areas. So I do like developing stuff. Thinking about how we can architecture our systems, but also really like thinking about and making sure that if we make a change in code or configuration, how do we get that into production as fast and safe as we can? So I kind of like to be in all of those fields at the same time. That's what I really love to do.
Yeah, I can relate to that. I'm feeling quite the same, working as an architect, but being also heavily involved with the DevOps team. So, and today you will be doing a session about serverless architectures, right? And event-driven KEDA. Yeah, I think without further ado, let's go to your session because we're really looking forward to it.
All right, cool.
Good luck.
Let me share my screen. Here's the one. All right, so for the next 35 to 40 minutes, we're going to talk about KEDA. KEDA stands for Kubernetes-based event-driven autoscaling. So KEDA basically is a component, a thing that we can install on any Kubernetes cluster. And that helps us then to do event-driven autoscaling on Kubernetes. Because as we will see in a bit, that is something that Kubernetes cannot do by default. So that's where KEDA comes in. And it really makes it simple to do event-driven autoscaling on Kubernetes, as you will hopefully find after the demos. So we already talked about me a bit, so we can skip this one. I'm from the Netherlands. That's probably the only thing we didn't talk about yet. All right, so before we dive into Kubernetes and KEDA, I want to go very quickly over what is a container and what is Kubernetes, so that whoever hasn't done anything with Kubernetes at all yet can still follow this session and can still see where KEDA fits in and what it can do for you. So I'll make it really quick for those who do have experience. So what is a container? A container is this very simple, lightweight package that contains whatever your application needs to actually run. So where in the past you had to install all the dependencies on a virtual machine, for example, to run your application, make sure there was a web server available, all that stuff you now put in the container, and all your virtual machine or your hardware now needs is something to run that container, a container runtime. As long as that is available, then your container will run there. You don't need all the specific dependencies of your application anymore because they are in the container, making it very flexible. But just having a container isn't enough, especially when you want to run a container in a production environment. You probably want stuff like high availability and fault tolerance and stuff like that. So we need something to manage all of those containers in production for us. And that's where Kubernetes comes in. It's a container orchestrator, and there are more out there, but Kubernetes is by far the most well-known and most used one out there. It's available on all of the bigger cloud service providers, etc. So Kubernetes mainly consists of two main components, which are the masters and which are the workers. And the master is responsible for making sure that what you want to run on your cluster, what you tell it to run, that it actually does run on your cluster. And the workers are then responsible for doing the actual work. That's where your application will actually run. And then if you want to run anything on your Kubernetes cluster, you provide your master with a definition on what you want to run. So you could, for example, give it a YAML file, which specifies the application you want to run. This is a very simple one. It's not even complete. I don't even think it runs, but you'll get the idea of how that would work. So you would have to specify a few things in this file, like what is the container you actually want to run? Here it's a Grafana container. On which port do you want it to run? And how many instances, how many replicas of your application do you want to run? So you create this file and you give it to the API of a master, and that master will then try to figure out where to run that particular workload and try to divide it over the workers you have available in your cluster. And it will then continuously try to monitor if the state you told it to be in that application, the YAML, if that's always the state in your cluster. So if in the unlikelihood event that a worker would go down because of a power outage or a network failure, for example, then the master would notice that you no longer have 3 replicas running, but then now just 2. And the master will try to get that fixed for you by moving that workload into another worker, making sure that it still fulfills your needs that you specified in the YAML file. So that's kind of the basics of Kubernetes and getting something deployed here. So let's dive a bit into how scaling works. So scaling in general could be done horizontally or in a vertical manner. By horizontal, we mean that we would add additional machines to our compute resources. So we could add an additional virtual machine or additional hardware. By vertical scaling, we mean that we resize the machines we already have. So we could be adding additional CPUs, we could be adding additional memory, stuff like that. If we then look at what there is by default in Kubernetes in terms of autoscaling, then this is kind of the table that we get. So there's again horizontal scaling and vertical scaling. And in Kubernetes, we can do that based on nodes or the pods. And pods are kind of the smallest thing that we can run on a Kubernetes cluster. For now, for the sake of simplicity, see a pod as just a container. So we can scale the number of nodes in our cluster, and we can also scale the number of containers, the number of pods that run on it. So in terms of horizontal, we can simply add or remove nodes or pods to get more compute resources if we need it. And in terms of vertical scaling, we could resize the number of the nodes, add more CPUs, more memory, etc., to the existing nodes we have in our cluster. And since we can also limit the amount of resources a pod is allowed to use, we could also play with that to give it more or less resources as it needs. And it depends a bit on where you run your Kubernetes cluster and which version, etc., which of these features you actually get, because not all of the Kubernetes versions on all of the cloud vendors, for example, have all of these 4 auto-scaling options available. So we would have to look into the documentation to find out what you can specifically use on your cluster. But the thing is always that this whole scaling thing that's by default in Kubernetes can only react to the symptom. It can only see, for example, that the CPU is going up or memory is running low, but it can't react to the actual cause of why that is happening. And that's where KEDA comes in, because KEDA can. With KEDA, we can do event-driven autoscaling and actually react to events instead of to CPU usage going up. We can also install KEDA on any Kubernetes cluster we like, in any cloud, on your local machine, doesn't matter. And that's very easy, very simple to do. with the Helm charts that are available for you. So this is a bit of an architectural overview of KEDA. So let's go through it. As you can see, KEDA only kind of consists of 3 components, and it really tries to leverage what's already in Kubernetes by default. So first of all, let's talk a bit about the scalers. The scalers are the things, the components, the little components that can read a particular event source. So for example, in the first demo later on, we're gonna see a demo of an Azure function that uses an Azure queue. So our Azure queue here is the event source. So there is a scaler that can read how many messages there are available on the Azure queue to do to get that metric and then do scaling based on that. So today there's quite a big list already available of scalers in KEDA by default. Here's the whole list of it. And as you see, there's quite a few on it that do some things with Azure resources. But although KEDA was originally created by Microsoft and Red Hat, it's not a Microsoft thing at all. As you can see, there's lots of scalers available for non-Microsoft related stuff. There's MySQL, there's Postgres, there's IBM stuff, there's Google Cloud stuff, AWS. So there's lots of scalers out there that could help you with the scaling stuff. So then when a scaler grabs a particular metric, KEDA then uses its metric adapter to expose that metric to the horizontal pod autoscaler in Kubernetes. So most of the scaling of your workload isn't actually done by KEDA. It's been done by the horizontal pod autoscaler that's in Kubernetes by default anyway. When I say almost all of the scaling, what I mean is that Kubernetes by default can only scale your workload from 1 and up and down to 1. So you can never scale down to 0 instances of a particular workload. With KEDA, you can. So that's the main role of the controller you see here in this image. The main thing that a controller does is scale down to 0, or make sure that if we want to scale up from 0, that happens as well. So that's a nice additional benefit of KEDA. We can actually scale from it to 0, and that is something that we cannot do by default in Kubernetes. But other than that, KEDA really tries to use whatever is available in Kubernetes already instead of doing that itself. So one important thing here is that a scaler will grab the metrics of your event source, like the number of messages on a queue, but it will never grab the actual message of the queue. It is still up to you, up to your workload, to do that actual work. So it's still your event source. What do I mean by that? This is kind of how KEDA works in that flow. KEDA, and then specifically the scaler, will reach out to the queue to find out how many messages there are on that particular queue. It will go back with that metric into KEDA, and then a potentially scaling of your application happens. And then your application needs to go out to the queue to fetch the actual data. KEDA is not going to do that for you. There are alternatives in the market to KEDA to do scaling on Kubernetes and scaling of serverless functions, for example. They do it a bit different. They do grab the data from the queue and then actually also pass that data into your application. And that's mostly done via HTTP. So the benefit of that second approach is that your application doesn't need to know anything anymore about the actual underlying event source. So your app doesn't need to know anything about queues. It only needs to know about HTTP. But the downside is that because you don't have to know anymore about the queue, you also can't work with the benefits that you get from that particular queue, like dead lettering out of the box, things like that. So there's trade-offs between the two, but KEDA, as I said, doesn't give you actual data. That's up to you. So the first demo we're going to look at here today is one that uses Azure Functions, because I really think, I hope you will see that in a bit, that combining Azure Functions here with KEDA is really a powerful combination. And we're going to run that on a combination of AKS, the Azure Kubernetes service, and the virtual nodes, which are then being backed by the Azure container instances. And here in this event-driven example, that's really a really good combination. And here's why. Imagine that you have a queue, for example, and that's being used to import data into your system. And sometimes 1 million messages are being added to that queue and need to be processed. But other days, there's nothing to do when nothing actually gets added onto that queue. So the workload there is very unpredictable. So if you would handle that workload on your default already proficient AKS cluster, you might be overloading that because that would have to rapidly scale out, add additional nodes, etc. It might be not be fast enough, so you might actually be impacting whatever is running on it yet. But with the combination of the Azure Kubernetes service and the Azure container instance, what you can do is you can give the workload to the container instance, or sorry, to the Kubernetes service, and when it needs to scale out, it will make the decision to see if should I run this particular workload on AKS, or should I run this particular workload on Azure container instances. So especially with this event-driven stuff, it will often make the decision to offload that work to the Azure container instances, have it eat the queue, and then just destroy all the containers that have been created on the Azure container instances. So that's a really powerful combination, because for you as a developer, you only need to talk to one API, to a single endpoint to trigger your workload. And then the two systems combined will make the decision where to actually run the workload. You don't have to do that yourself. That's really cool. All right, so let's dive into a demo there. So since I'm going to show you how to run an Azure function on Kubernetes using, and then scaling that using KEDA, we're going to use the Azure function CLI to create a function. And this is how we can do that. Func init in the current folder, and then specify that we want to run that in a Docker container. As you can see, you get the choice to pick a particular workload. Azure functions aren't just about .NET or Microsoft or C#. There's other options as well. So now that I've initialized that, we're going to create our first new function. And then we get to pick how we want to trigger that particular function. And as I mentioned before, in this first demo, we're going to use the Azure queue. So I'm going to pick option 1 here to go with the Azure queue. Let's come up with a very original name here. And it's going to do some templating here to get that function going. And as you can see, there's quite a few other event sources, triggers available for you to use. All right, let's see what it came up with. Let's blow that up a bit. All right, so the first thing you will notice is that we actually have a Docker file, since we're going to run this Azure function in a Kubernetes cluster. And it uses the Azure function base image. And second thing is that we now have our Azure function right over here. And for those who've never seen an Azure function before, this is kind of all there's to it. The thing has a name in this attribute. And then here is the trigger defined. So we pick the queue trigger. So you will see that here as well. And this run function is your entry point into this particular function. So all I need to do now is specify what is the name of the queue we want to use, and then specify the connection string to that particular queue. So when we would have done that, you could be deploying your application. Let's quickly look at how we would do that. So the only thing you would really have to do here to get it working is specify your connection string. I'm going to leave that out for now. If we want to deploy this particular application, we could again use the Azure CLI and run this particular command. We have to give it a name. So let's use again the very original one, KEDA. And we would have to specify the registry. that we want to use and that we want to put this container image into. So here I'm using my own. And if I would now hit enter, what would then happen is that it would in the background start to build the container image in which my Azure function would live. It would then push that out into my registry. And it will then tell my Azure Kubernetes cluster to start deploying and running that application. And that would all happen in the background for you. But if you actually want to get a bit more control over what's happening there, then you can do something like this. We could output whatever's being done there in the background into a YAML file to see what's actually going on there and to be a bit more specific in what we want to do there. So let's move over to another window here, because I've already done that and already created the image, etc. That sometimes takes a bit of time, so we did that beforehand. So when you would have run that command that we saw in the previous window, you would end up with this deployment YAML. And that specifies what should be run on your Kubernetes cluster to get this function running. So if you've ever worked with Kubernetes before, this should be kind of familiar to you, because this over here is just a secret. And this now contains my connection string into my Azure queue. Here's the deployment, which specifies what I want to run on my Kubernetes cluster. So that's actually my container image that contains my Azure function. This again is just default Kubernetes stuff. But down here is where you see a thing that is specific to KEDA. And that's the scaled object. That's a KEDA specific thing. And this is where you specify how you want to do the scaling of your particular workload. So down here, it specifies, again, the trigger I want to use. So for example, here I'm using the Azure queue trigger. It says triggers, so we could actually have more than one trigger. That's available since version 2 of KEDA, which was released just a few weeks ago. So we can now have multiple. And per trigger, you need to specify a few parameters to make it know how to actually do the work. So you would need to specify where does it get its connection string, which queue should it actually be watching, stuff like that. There's also a few additional interesting settings that you can use here as well. So for example, here's the polling info that will specify in how many seconds KEDA will reach out to your queue to fetch the particular metric. I set that to a pretty low value here because that's easy in demos. And you also get to specify, for example, the minimum and maximum number of instances you want to run of your, in this case, Azure function. And that's a cool thing because you now also get to limit the scale out. And that comes in handy because if you would let this scale out to 1,000 or 10,000, which could easily happen, you would probably overloading your SQL database if you would need to call into that, or your Azure storage account or whatever. So it comes in handy to be able to limit your scale out here. All right, so that's kind of how this file is being built up and what needs to be put in place to do an actual deployment. So now that we have this YAML file, we can actually be deploying this into our Kubernetes and get that to work. I already did that because it could take a bit of time. So let's have a quick look at what it looks like if we put it into action. So as you can see, it's already been deployed here on my Kubernetes cluster. It's the one over here. All right, so let's have a look at some internals of the particular cluster. If we look at the particular nodes, then we should see that there is an AKS one. So that's the AKS node. I have only one of them. But as you can see, there's also the virtual node. So you can see here that there's actually the combination of AKS and the Azure Container Instance. So what we could also look at is the fact that there should not be any pods running. So as I mentioned before, we can scale down to 0 with KEDA. That's something that you cannot do by default. So that's why it says that there's nothing running here, and you also see that here in the background, there's 0 out of 0 running. But if we then look at the horizontal pod autoscaler definition, then you see that it actually has been created for us. It needs to reference the deployment we just saw in the YAML file. And what you see over here is that it does still say that it has a minimum pods of 1. And that's because Kubernetes cannot scale down to 0 by default. It took me a few hours to figure out why that was when I started out with KEDA. I hadn't noticed that particular thing. So this is actually what you want to see. That's normal. All right, so let's have a look at how that scaling would actually work then. Let's have a look at a particular deployment. So as you can see, the deployment is there, and there's 0 out of 0 instances ready here. So if I would then give a bit of workload to my particular queue, then we should see that something actually starts going. So what I did here is I created a very simple application that can put a number of messages on the queue. So let's have that running. And it should say somewhere down the line, so it's done. There we go. Yes. All right, so we already see that KEDA picked it up and already started scaling our workload. And it will continue to do so till our queue is actually empty. So let's head over to the Azure portal. And then we can see something interesting here, and that's that, as you can see, there's already 4 instances of my Azure function on the cluster. And what you can also see is that one of them was being deployed to AKS, to the AKS pool, and the other 3 were actually deployed to the virtual node. And as you can see here, the one that was deployed onto AKS started pretty quickly. It only needed a few seconds to get an IP and actually do some work. Whereas the ones on the virtual node are still pending to spin up. So they do take a bit of more time to get up there. And if you would refresh, then you see that there's also one on the virtual node now running, but it did take a bit more time to get that done. And let's see, it scales up to 8 right now. And what you probably see quite quick here is that it also starts scaling back to, should be scaling back to 0, because it then processed all the events. It should be scaling down rather quickly. There we are. So it already started scaling down again to 0 because there wasn't any work left to be done. All right, so that's the first demo on how to create an Azure function that will read a queue, get it deployed into your Kubernetes cluster, and then use KEDA to do the actual scaling. Let's have a quick look at another example. And as I mentioned before, you can actually run KEDA on top of any Kubernetes cluster. So you now saw a combination between AKS and the virtual nodes, the Azure container instances. But the next demo I'm going to do on my local development machine. And I'm doing that using a combination of K3s and K3D. And K3s is actually a lightweight version of Kubernetes. They replaced some of the main components with smaller ones. And that makes it very lightweight, being able to run on your development machine or even Raspberry Pis, for example. And then you can use K3D to actually run Docker inside of Docker, which allows you to run multi-node Kubernetes clusters on your local machine. And that's really handy because then you can do testing, etc., developing on Kubernetes on your local machine with still having a kind of identical Kubernetes cluster with multiple nodes to test stuff out. So the next thing we're going to look at is a combination of how we can do scaling with KEDA based on data, based on metrics that we can find in Prometheus. And Prometheus is a time series database where we can store a lot of metrics. And we can then query that database using KEDA and do scaling based on that result. So what I did here is I created a .NET Core API, and that API exposes Prometheus metrics on, for example, the number of requests in the last minute and the duration of those requests, etc., etc. And so KEDA then reads those metrics from Prometheus, and when certain thresholds are met, KEDA will start to scale the API to start adding more and more instances. So let's have a look at how that would, what that would look like. Let's go down to this one. So the first thing we probably should look at is the startup file of my controller to let you see that adding Prometheus is actually pretty simple. It's installing a few NuGet packages and then adding some default configuration here. And when you've done that, then it will start exposing some default metrics by default. So the ones I mentioned before on number of requests and execution time, etc., those are exposed by default. But you can also add your own metrics. So I did that here in this particular example, where you can do observes, and you can also do increment particular counters, for example, if you want to. So you could be counting the number of orders, things like that. And the data again will be exposed to Prometheus, and Prometheus will start reading that particular data, and then you can use that to do scaling. So let's have a quick look at the scaled object to see what that looks like. So it's kind of similar to the scaled object we saw in the previous demo. The main difference here is that we have a different scalar type, since there's now Prometheus. And that also means that we have a few different settings that we can use to actually make that work. So let's see that in action quickly. Let's switch clusters. And let's make sure this stuff runs. So this should now be my API. This should be Prometheus. Yes. All right, so this is the default dashboard in Prometheus that you get, and that allows you to query the data in the database if you want to. So we're going to use that today to track the usage of the app. So I have already specified a particular query here to fetch the data, and this is actually the same query as that KEDA uses to do the scaling. So we're going to look at the request duration over the last minute, and if that exceeds a certain threshold, then KEDA should start scaling out the application. So let's see if it actually does by looking at the scaling again of the object, the deployment. So as you can see, this is again my sorry, it's this one again. This is the application, the .NET Core one. As you can see, there is one running this time, because for an API, it probably makes sense to have it live all the time so that you can actually get a response quickly. And if I would now try to make requests against that, if I would be in the correct directory, let's do it again. So I'm using a Go command line utility called Hey to trigger some load on that API that I've been written. And so if we would now go back here, then we should probably see a bit of data, which we do not. The API is up. Is it? It is, all right. There we are. There is a bit of delay between the metrics that are exposed and how quickly they end up in Prometheus. I guess by default, it it tries to fetch metrics every 15 seconds or so. So there's a bit of delay. But what you see here is that the number of requests actually go up. And that should mean that we also see that KEDA started scaling our particular application, because I think I've set the threshold to 3 or to 5. And we are definitely going over that. So as you can see, KEDA started scaling this particular API based on the metrics. And since we can do scaling on Prometheus, and Prometheus is a tool that's very widely used in open source projects, and we can kind of write a lot of metrics into Prometheus, we can also do scaling based on a lot of things. As long as we can write anything into Prometheus, we could actually do scaling based on those metrics. So that makes it a really powerful combination to do your scaling workloads. All right, so the last demo I have for you today is about how we would be able to, or how you can handle long-running tasks on Kubernetes. And that requires a bit of introduction, probably. So imagine the following situation. We have, again, our Kubernetes cluster in Azure, for example, and then we have masters and we have workers. But at a particular point in time, your cloud provider will probably make the decision to update your workers. There is operating system patches that need to be done, things like that. So what happens then is that your cloud provider will decide that it will spin up a new worker for you. And once that has joined your cluster, it will destroy other older workers and you simply remove them. But what happens if you've been running long-running tasks on any of those workers? So imagine you were doing some video decoding, encoding on that particular worker, and that process could take over hours to complete. If then the cloud provider would decide to kill your particular instance, that work would be gone and you would have to restart it. And continuing in such a process is probably pretty hard. So you probably need to start over all the way from the beginning. So how can we handle things like that in Kubernetes? So by default, if you want to, what happens when a node is going to be removed, then a signal will be sent to your container to notify that it's going to be shut down. And by default, you have like a 30 seconds delay between being sent that signal and actually being shut down. So that gives you 30 seconds in which you can close connections to databases, things like that. And that's okay for APIs, etc. Then 30 seconds is probably enough to finish the ongoing work. But if you are doing long-running tasks, that's never going to be enough. And there's another problem as well. Somewhere in those 30 seconds, you already lose connection to your container. So you can't reach that container anymore, which means that you can't do monitoring of that container anymore, for example. So that's all not too ideal for long-running stuff. But luckily, there is something on Kubernetes that is called a job or jobs. And it also comes with a job controller, and that will ensure that one or more pods are executed and successfully terminated before that node is being shut down or removed. So a job does kind of give you the guarantee that whatever you run inside of a job, that will finish until the end, even though a node might have to be restarted. That will wait for your job to be completed. And the pods are then, the pods that are being run in a job are only being cleared and cleaned up when the job has been completed. And the beauty is that KEDA can actually also do scaling based on jobs. So let's have a quick look at that as well. Let me get back my editor. There we are. All right, so again, I created a very small example for this one. It's even smaller than the other ones. So what I did here is I created a console application in .NET Core. And that console application will reach out to my queue, fetch an item, and then do something, and then die. So this is where you would normally do your long-running task. And this is again a demonstration on that KEDA can kind of scale any container. It doesn't really matter what's in there. I mean, this is just a console application. As long as it can run in a container, KEDA can kind of scale it. So that's what you see here as well. So what's going to happen here is that I've already deployed this YAML, this deployment YAML, and this time the thing we are going to deploy is a scaled job instead of a scaled object. And in this file, you specify how the scaling should be done. So again, there's some settings on the polling and the fall, etc. There's also settings on how many parallelism do you want to do and how many completions can a particular job do, stuff like that. And then probably the most important stuff is what is the container you want to run inside of the job to do the actual work. And last but not least, of course, there's the trigger section, which again specifies that I want to trigger based on a particular Azure queue. So there's a message on the queue that needs to be handled. And this time it has a different name compared to the other one. So let's see a quick demo on how that works here as well. So let's do a kubectl get jobs. All right, so as you can see, nothing is currently running there. Nothing is currently processing anything. But if I add a message to this particular queue, then it shouldn't take too long before, and there we are already, before KEDA saw the message being put in the queue and it started scaling this particular job. And it shouldn't take too long, and there we are, for it to complete and be done with this particular job. So we can actually also go into that particular thing, Kubernetes GTL, logs, job, there's that one. And you see that it actually put a message in the logs that contains whatever I have been putting in there, which is again, oh, let me find the other one. Here we are. It's just this specific line down here. So it got the message from the queue, processed it, and then died and waited for something else to be put on that particular queue. All right. So that's what I wanted to share with you today on KEDA, Azure Functions, and doing autoscaling on Kubernetes. Here's a bit of contact information if you have any questions after the session or want to reach out. There's a blog post on my blog, edwinstyle.nl, which goes through the first demo I did. So it will go through setting up a Kubernetes cluster, creating that Azure function, getting it deployed, etc., etc. So if you want to redo that first demo, then please go there. You can actually find all the demos and the source code that I did today on my GitHub repository. So if you want to do them yourself or want to look into them, feel free to find them there and use them for your own good. So thanks for joining me, and let's see if there are any questions.
Thanks so much for this great session, Erwin. Yeah, there were a few questions, and one of them you've already answered in the end of your presentation about long-running tasks, so thanks for that. But another one is how fast will a container actually start when you use KEDA? Is there like a cold start time or any delays?
Well, there isn't any other delay than you would normally have if you would start to run a container on Kubernetes. With the one exception that in the definition, in your scaling definition in KEDA, you have this polling interval. Because what KEDA does, if you use, for example, an Azure queue, the polling interval will be used to specify how many seconds to wait between each call into your queue to fetch the number of metrics. So if you would set that number to 5 minutes, it could take 5 minutes for KEDA to pick up that there's a message on the queue and to start scaling your workload.
Yeah, exactly. So what's the minimum time you can set there?
In 1 second.
Oh, 1 second. Okay. Well, that's great.
I'm not sure if you should do that in production though, but you can.
All right. Okay. Well, thank you for this question. Unfortunately, we're out of time with the next speaker waiting already. So thanks a lot for being here, and hopefully we'll see you next time.
You're welcome. Have fun today. Bye-bye.
Yeah,
Thanks. Have a good
thanks.
day.